to determine whether a steep slope or a gradual slope will have a higher speed, and to prove your theory as to which one does, which one doesn't, or some alternative. Now, you want to notice that the height stays the same. So I gave you a visual example of this, which you can't see, but let me have my at-home students see it a little bit. So an example of this would be a shallow slope and a steep slope, but I want you to notice that they are being dropped from the same height. So the height stays the same. You want to see which one is going to have the higher speed at the bottom. This is a roller coaster design experiment that you're designing, and we're going to do a roller coaster problem today. This whole worksheet is on one roller coaster. So let's just do a warm-up. I want you to try it on your own. I'll give you some time to collaborate with your partners. Again, there's multiple ways to design this experiment to get accurate results. I just want to give you some information on the parts you've been using. You know they have springs. You know they have this little divot right here, which is called a force sensor. And within it, it also has a position, velocity, and acceleration sensor. So there's a lot of capabilities in these cards that are at your disposal. So motion sensor, which calculates position, velocity, acceleration. We've got a force sensor in here as well. And then obviously the very basic tools of rulers or anything else. If you decide that you want something else to include, these are pretty frictionless parts, and these tracks provide nearly frictionless motion, so you can think about those as well when you put this together. The first one is just to tell me what you think. Which one will have the fastest speed at the bottom? Is it the steep slope or is it the shallow slope? Again, they are starting at the same height, not at the top of the ramp. So if this starts here and this starts here, which one is going to have the fastest speed at the bottom? What did you come up with when you collaborated with your groups? Steep slope. Any other thoughts? Same. This is what students usually come up with. Why is this a misconception? Can anyone explain to me why? It's a short distance. So this is the key thing here. It does accelerate faster. So the acceleration is faster or larger. Faster is usually associated with speed. But it has a shorter distance to travel. This one for sure is going to accelerate pretty slowly, but look at how much longer this ramp is versus this ramp, right? So again, a common misconception. This is one of the problems that are most commonly missed because most students think that just because it accelerates faster, it must be going faster at the bottom. The speed must be faster at the bottom, which is not true. It is going to have the same velocity at the bottom. Can anyone tell me why? What concept that we learned in this class is important to understand that? Ian?
Calculate gravitational potential. You don't take into account angle.
Good. So we've got gravitational potential energy. At the bottom, you have kinetic energy. This is conservation of energy. So if I know I start with 3 blocks of GPE, I should end up with 3 blocks of kinetic energy. The amount of energy you have at the beginning is equal to the amount of energy you have at the end. But as Ian said, the equation is mass times gravity times height. There is nothing in that equation about angle. Doesn't matter. So as long as the height stays the same, this height is equal to this height, you have the same speed at the bottom. Speed here is kinetic energy. And again, the mass is going to stay the same, obviously. Gravity is going to stay the same. Therefore, height is what is proportional to your velocity squared. So that is the only factor that can change your speed at the bottom. Okay, regardless of how you answered this question, you still should have been able to come up with a good experiment. So can anyone offer me an experimental design? So the setup is one steep ramp, one shallow ramp. They're gonna be at the same height, right? I gave you some hints here. Emily said to set it up so that the spring is at the bottom. Does this matter? The spring, it could be this way. It really doesn't matter because we're not asking about elastic potential energy. And if the force sensor was at the bottom, we don't need force either. All we need is what aspect of our cart to be turned on. We're going to set it up to Pascal, like Emily said, but what different variables need to be turned on in our cart? The velocity. This is the easiest way to do this. If you turn on the velocity, you're going to be able to graph it because you still need to tell me how you're going to analyze your graphs, right? What is my graph going to look like if I start at 0 speed and start moving down the ramp? It's going to be a steady increasing velocity. It'll hit the end of the ramp and then jump down to 0. Maybe it'll bounce a few times. And what are we looking for to find out what the speed is? We want the max value. So that's how you're going to gauge what the velocity is. Are there any other methods that would work though? In the last frame. Good, good. You could do it frame by frame and see the distance in the last frame. I like that. You're assuming that those frames are equal amounts of time. Perfect. And what's also nice is that these ramps have rulers on them. So we don't even need the ruler aspect of it. You just need to, frame by frame, see where it starts and stops. A few things that I'm going to adjust from this point on is the fact that we're going to consider any chemical, so these are non-mechanical energy types. Non-mechanical energy is energy we cannot calculate. We're going to leave these out of the system. All my blue is running out. So this would be considered chemical, energy from a person, a machine, a battery, or a motor, and then energy that results in thermal energy. We don't have an equation to calculate those two energy types. What we do have equations for are what we call mechanical energy. So this is what we're going to include in our system, which would be elastic potential energy. We're not using that today, but you know the two equations for EPE. So this has two equations. We've got kinetic energy, which is motion, and we've got gravitational potential energy, which is due to height above the ground. I want you to notice something. In our diagram, they define the height for you. So they tell you the height at 0 is not necessarily on the ground. It's the lowest point of your roller coaster. And then we've got our maximum height at 40. So you have these values for gravitational potential energy. Height is given. You've also got the fact that there's no wind resistance and no friction. They're not important. We're not going to take that in consideration. And the velocity at the top of hill A is equal to 0. Anytime we are doing these LOL charts from this point on, I want you to consider non-mechanical energy as outside the system, and then mechanical energy inside the system, because this is something we can calculate. So my system here, I'm going to define for you as the coaster, the ramp, and the earth. You need earth to have gravitational potential energy. You need the coaster because that is moving and it creates kinetic energy. The parts that I want you to graph yourself in this LOL chart is A, B, C, and D, and E positions. But let's think about where that energy comes from. If we start our chart at A, there needs to be something that gets it up to that position, right? You guys have ridden many roller coasters. Maybe some of you haven't, but I suspect many of you have. What gets a roller coaster to the top before it starts moving due to momentum? It's chemical. Chemical due to the motor. We're not going to consider the motor part of the system because we don't want to include anything that is not calculable. But I am going to say that the energy coming in, we're going to make it 4 blocks, is chemical energy due to the motor. This sets you up. From that point on, you should be able to determine what type of energy is in each individual part. And I want you to think about our very, very important concept of conservation of of energy, which means energy is never lost, only transferred. Okay, you guys know how to calculate energy. We did that for the homework last night. Now we're combining it with conservation of energy, the fact that the energy coming in is equal to the energy at A, B, C, D, and E. As you do these problems, you're going to look at the question and you're going to say, is this too easy? Am I doing something wrong? It's not. You're not doing something wrong. A lot of these answers are not calculations, they're conceptual, okay? So if you feel like it's too easy, it is pretty easy once you get the concept. Okay, any questions before we start? Okay, your homework is a concept builder. It is very similar to what you did in class with gravitational and kinetic energy transfer. And it'll help you prepare for the quiz. On top of that, you also have the corrections with a video answer key. You're going to do 2 parts, the apprentice and the wizard level. You have all kinetic, all gravitational, and then some portions in between. When it says potential energy, in this scenario, potential energy means gravitational energy, not elastic. And then you can count these blocks to find the ratios in between. I am going to have a tutorial virtually if you want to pop in, and we can work on this concept builder together.